So now I'm going to talk a bit about the Keras functional API, and I'm going to use transfer learning as a motivation for that. So this will be also the exercise you're going to do today, which is to use the classification network you trained last week for classifying the fashionist examples and apply that one to MNIST. So we're going to transfer what the network learned with the fashionist images and use that to extract features from the MNIST images. You're going to use a function API for that because the sequential API that we used before, even though it's very easy to use, it's not sufficiently flexible for the kinds of operations that we're going to need here. And the functional API is going to be helpful also in the first assignment. The first assignment uses a simplified data set, so you will not need to do sophisticated networks like we saw before, but still you can experiment a bit with your networks, and the functional API may help you do things a bit more flexibly. But let's start with this idea of transfer learning. I'm just going to give a brief overview. The idea here is that we can share something that we learned in one particular problem and use that in a different problem. For example, suppose that we are training a network for image classification, and there are lower level features like edges and curves and straight lines and so on that can be extracted for the images, and they will probably be the same whether we are trying to distinguish cats and dogs or horses and donkeys or other types of animals. The kind of basic features that we are extracting from the images before passing on to the classification layers, those dense layers, will probably be mostly the same. So it's likely that if we have a large data set of cats and dogs, we can use a network trained in that data set to help us classify, for example, horses and donkeys where we have fewer images. Or we even can share some higher level representations. For example, the kind of structure in grammar, in sentences, and so on is the same for different speakers of the same language. Even if at the lower level, the extraction of features from the sound to convert them into words may have to be adapted to each speaker. So we can use the same kind of network or classifier at the higher level and just learn the lower level transformations to map the voice of each speaker to the appropriate words. So this, the basic idea here is that we may want to use some part of a large network that we created into a new problem. And now there are different things here that can happen. So under this large umbrella of transfer learning, we can have different kinds of problems. For example, we may want to do basically the same thing, but in a different domain. This is generally called domain adaptation. For example, we have this is quite used nowadays, sentiment analysis, trying to infer from what people write, for example, comments, reviews, and so on, if they were pleased or displeased or angry or happy, and so try to automatically extract some information about what the people were feeling from what they wrote. Now we can do this, we can train on a large data set, for example, with movie reviews, and now we want to adapt this for our shop that sells electronics or appliances, something like that. We would be adapting this to a different domain, so there may be some differences here, but the basic problem of trying to understand the words people are using and what they are feeling from those words would still remain the same. So this would be one example where we could use what was learned in a supervised manner in one domain and to help us solve the problem in a different domain. This is also a case where we could use unsupervised learning. So we could look at many different texts, even if we don't know what the sentiment was there, to help us encode that data better. And here we can use, for example, autoencoders, denoising autoencoders, undercomplete autoencoders, and so on, which we're going to see next week. So transfer learning is not something we only can do with supervised learning. We can also bridge the gap between unsupervised learning and supervised learning by transferring these so methods for extracting features, embedding the data, and so on from one area to the other. But we're going to see more on that, autoencoders, for example, next week. Another problem that may appear, and it's similar to domain adaptation, where we have to do some kind of transfer of knowledge from one case to the other, when there are gradual changes over time. So this can be because of changes in the actual distribution of the data, or in the relations between the data and the desired predictions that we want. For example, changes in the economy may make it so that when you're trying to predict the credit risk of some client that is trying to buy things from you on credit, the relation between the features of the client and the risk of not being able to pay you will probably change as the economy gets better or worse. So maybe you'll need to relearn or to adjust what you learned about this mapping. So this is similar to the problem of transferring knowledge from one problem to the other, but it's a bit different in the sense that you are dealing with the same problem, but things keep changing over time, so you may have to fine-tune your network or retrain it or something like that. Also, the data distribution can change. So if you start with a small company, the distribution of your customers may be different than when you have a very large, very popular company, and it no longer caters to a specialized group of people, but now you have commercials on TV and so on. And so the distribution of the data that you have for your customers may now be different, and you may need to relearn things. So in this case, concept drift, sometimes we cannot really transfer much information if the changes are very big, and we have to really retrain our models again, or we can start from the previous iteration and just fine-tune our model and still reuse something that we had. But the idea here is just to understand that you can have different kinds of situations where you need to learn something new, but you can still use what you had learned before. So basically, in transfer learning, we're going to, in the context of this course, we're going to take advantage of models that were previously trained in other data sets. For example, you can use image recognition networks that were trained on ImageNet, which is a very large data set with 1.2 million images in 1,000 categories. So these networks can be very powerful because they have a lot of data to train in. But training these networks is beyond the hardware capabilities of most of us. We don't have computers to train these kinds of networks. So we can use these networks to extract features from our images, and then use those features by coupling that part of the network to some classifier that we're going to train and adapt to our particular problems. So we can do this by breaking down the model and the problems. We can train parts of the model. We can start from previously trained parameters and fine-tune those parameters, or we can even freeze parts of the model and then just train other parts. We're going to see an example of that in the exercise today, and we're going to do that for the assignment too, optionally. Okay, so the exercise would be to use transfer learning to take advantage of the network you trained on fashionist to help learn to classify the MNIST dataset. So last week we looked at this dataset, fashionist, which has these cartoons for the clothes, and the exercise was to train a classifier using convolutional layers and then the dense layers in order to classify these images into the 10 different classes. And now what you're going to do is to take the network you trained on this data set and use the same convolutional layers. You're going to use all the convolutional transformations of your previous model to extract features from the MNIST dataset. And the rationale for this is that your network had to learn to identify edges, different inclinations of the contrasts here, and so on, in order to generate the appropriate features for the dense layers to classify these examples. If you use the same convolutional part of the network on these examples, the digits, you are also going to extract features regarding the orientation of the edges, the contrasts, and things like that. And in theory, these should be enough to train the classifier, the top of the network, so the dense layers, to now use those features to classify the MNIST. And this is what you're going to do using the functional API. So the model that you trained last week, you already have a network that is fully trained with fashion MNIST. We are now going to create the same graph as before, so exactly the same model, but we're going to use the functional API so that after loading the weights from the trained model that we have from last week, we can fix or freeze some of the weights, all the convolutional parts we will not be retraining, and then we can also throw away the final part of our original model, which were the dense layers, and replace those with a new set of dense layers that now we're going to train to classify the MNIST dataset. So this is how we can do. We will start by doing exactly the same processing of the data that you did last week. So if last week you divided the inputs by 255, you do so again. If not, then don't do it. But you have to pre-process the data in the same way, because we are going to use the first part of the model you trained last week. And so the data must be inserted into the model in exactly the same scale, format, and so on. But the difference is that now we're going to use the MNIST dataset and not the fashion MNIST dataset. So if you do this rescaling, everything gets scaled between 0 and 1, so you don't need to use standardization. If you use some other rescaling in your model last week, then do the same thing now. The idea is that you need exactly the same format and the same range of values getting into the first layers of this week's model, because those first layers will be the ones you got from last week after training. Okay, so now we're going to use the functional API. All of these layer objects that Keras provides, that we used last week to add to the sequential model, these layer objects also implement this special call method, which means that they can be used as functions. We can call them. And when we use them as functions, they will create the necessary operations and return the appropriate tensors, so that then the whole computational graph can be built and run by TensorFlow. So what we do when we use when we create a model like this is we start with an input layer. This is just this input class just creates the initial tensors that we're going to need. So we specify the shape. In this case, we are dealing with matrices that are 28 by 28 by 1, which are the images for the MNIST data. And it's the same shape that we used for the fashion MNIST classification. And we are going to give a name to this layer. This is useful because then we can go get the layer by name if we want from our model, or we just store that in a variable here. And now to use the functional API, we're going to create objects of the different layer types. For example, a 2D convolution with a 3x3 kernel, 32 filters, same padding, and so on. We can, in this case, this is actually not necessary because we already have the inputs there. So we create this layer as we did in the previous, in last week. but now we're going to call this object and execute it on this input. So this was the input layer that we created here. And now Keras will connect these two tensors, and now we keep doing that. We have the activation that is going to operate on the output of this function, so the tensor coming out of this function. We are going to feed that into the activation object, and then we're going to feed the output of that function into the batch normalization, convolution 2D, and so on. So using it functional API this way, we can do the same thing that we did with the sequential API using the add method, but the syntax here is different because we are calling each of these layers as functions on the output of the previous layer. So far, this doesn't give us anything new with respect to the sequential API. But now things get a bit more complex when we want to take advantage of the convolutional layers of the model we trained last week, but discard the dense layers. So first, since we are going to input load the weights of the trained model from last week, we need to create the complete model. So we're going to add the dense layers, the activation, and the softmax layer, and so on. We need to create the model exactly like we did last week. But the flatten layer here, we're going to give it a special name. This is the set of features that we're going to extract with the last week's model, and we're going to feed into the part that we're going to train today. So here in this code, this part and everything in the back here, we have the complete model exactly like we created last week. So now we can create a model using this chained set of layers, and we do this by calling the model class and specifying where we start and where we end. So the output would be this layer here, the inputs would be this variable that we created here with the input layer. So this model that we create here, the old model, will be a model that goes from the input to the output of last week's model that we have already trained. And now we can compile it. So this Keras will now create the actual model, the graph for the computation, and so on. And note that I'm just using as the optimizer stochastic gradient descent and loss mean squared error, which doesn't make sense for this kind of problem with a classification problem. But it doesn't matter because we are not going to use the complete model. We are not going to use this part. So this is just because I need to give something to the compile method when compiling the model. So I just give it these options and don't care about that part anymore. What I'm going to do is to load the parameters that we saved from last week. So remember that in the exercise last week, I asked you to, after training, save the weights of the model. Now we can load the weights, and as long as the model is exactly the same, the weights will all fit together in the correct layers and everything will work. So you need to recreate the same model that you used last week. And now we're going to freeze all of these layers. So in this model here, we can iterate through all the layers. We have this iterable here called layers in the model object, and we're going to set the trainable flag of each layer to false. This will mean that when we are going to fit anything that passes through these layers, the parameters there will not be changed. They will remain frozen. Okay, so now we're going to create our new model. And what we're going to do is to create a stack of dense layers. You see we have dense, ReLU, batch normalization, dropout, another dense layer with 10 neurons, and the softmax activation. So this is just the classifier head at the end of all the convolutions. But we're going to use as input for this one, we're going to get the output of the features layer from our previous model. So you see, I'm going to apply a dense layer with 512 neurons to the tensor that is coming from the layer called features in this old model object. And this layer called features is the one that we created here in Flatten. You see, we named it features. So I could also have used the output of this tensor here, but it doesn't matter. We can also, this is just to illustrate how we can identify a specific layer in our model. And what this means is that now I have a part of the computation graph that can be created starting from the input of the old model. So this output attribute here is the actual tensor that outputs from the layer. So this is the layer that I used as input for the old model, which was this initial layer here. And now I'm taking the tensor that outputs from that layer and specifying that in my new model, the input will be on this tensor. So I'm going to feed into this tensor. And then I'm going to create all the computation graph that results in this output here. So this creates a model that goes through all the convolutional layers of the old model, which are frozen by these instructions. They will not be trained, but branches off at this layer, ignores this part of the old model. We are not going to use it. It branches off at this layer and passes through these new dense layers. And this will be the new model. Will be a composition of, or a combination of the frozen layers of the convolutional part of the old model we trained last week and new dense layers that are going to be trained now. And now I can compile the model, create the appropriate optimizer, for example, stochastic gradient descent with momentum, the appropriate loss in this case, because now I'm going to train it, so I really need to make this right. This is a classification, multi-class classification problem with softmax, so I'm going to use categorical cross entropy, and I'm going to fit the model. And if you call the summary after compiling your model, you see that you have a total the total parameters here, but the trainable parameters are fewer. You have these 60,000 non-trainable parameters, which correspond to the parameters on the convolutional layers that we froze here. So everything that belonged to the old model is frozen. So in the new model, these would be the non-trainable parameters. Another thing that we can see here is that in this case, since I'm using a very large number of neurons in the dense layer, actually most of the parameters of the model are in the dense layer. And this is something that may seem counterintuitive, but it happens a lot in convolutional networks, is that the more you do convolutions and pooling, that is, the more you are shrinking the feature map, the fewer parameters you will have on the network. So it's possible to add layers to the convolutional network and reduce the total number of parameters because of the impact this will have on the dense layers at the end, if you are dealing with classification problems. So you can see that at least in this network, most of the parameters are in the dense layers. We can adjust that by changing the number of neurons here, or by adding another pooling operation or something like that. But this is a general aspect of these kinds of networks, is that convolution operations take usually far fewer parameters than the dense layers. Okay, so now we can do this and compare the training with the alternative, which is just to train everything from the start on NIST. So you can see what you gain or not with transfer learning from fashion NIST to NIST. Okay, so now moving on to the first assignment. The basic requirement I used for this assignment was to minimize the demands on the hardware for training these networks. And since training deep networks for image classification and segmentation using realistic data sets requires lots of memory because you need a large number of data. I created a data set that is not very realistic, but at least it you can use to understand how to solve these kinds of problems. So let's say that there are Pokemon close to FCT. We have photographs of them appearing in different locations. And this is your data set. These are images of 64 by 64 pixels. There are 10 different Pokemon types. The types are grass, water, fire, and so on. There are several Pokemons per type, so there are more than 10 different Pokemon in the dataset, but we are going to look at the types of Pokemon. And we also have in the dataset the ground truth for the segmentation masks. So for this image here, we have the region that corresponds to the Pokemon. For this one, we have the region that corresponds to the Pokemon, and so on. So this is the data that we have. The Pokemon images, these photographs, which will be the input our networks will then use in the future to do the predictions. The segmentation masks for training the segmentation networks, and also tables with the main and secondary type of each Pokemon. So each Pokemon has exactly one main type, and some Pokemons have an additional secondary type. So Pokemons can have one or two types when we include the secondary. This leads us to three different tasks that you're going to do in the assignment. One is multi-class classification, which is to predict the main type of a Pokemon from the image. So you get an image like this, each of these frames, and you predict what is the type of the Pokemon there. This is multi-class classification because each Pokemon has exactly one main type. So you use the appropriate loss function, the encoding, and so on to predict the class of the Pokemon. Another different task, although the network may be similar, is multi-label classification. If we consider both the main and secondary type of Pokemon, then Pokemon can have one or two of these labels, and this is no longer a multi-class classification problem because we cannot not assume that it only has one class. It can have two labels. So here the loss function is different, the activation is different. You need to understand that part, but you also have this information for each image. What are the one or two types for that Pokemon, and you need to create a network that predicts those types. And the third task is semantic segmentation. You want to identify in the image what are the pixels that correspond to the Pokemon. So this is semantic segmentation, but you only have two classes, either background or Pokemon. You don't need to distinguish anything else. So this is basically for each pixel, you can consider that you're doing a binary classification, and you can have any combination of pixels. So it's as if it was a multi-label classification problem where the labels are on all the pixels on the image. So you will have to think about the networks that you're going to use, what are the activation functions, what are the loss functions, and experiment a bit to try to optimize your results. The data is provided in a zip file. You have this online along with the instructions, and you can download the zip file, extract it, and don't change the structure of the folders there. So you have one subfolder called dataset that has the images, a CSV table with the data for all the images in the same order as the image, and also a text file with a list of the Pokemon types, because you also have in the CSV the index of each type, which makes it easier for creating the training set. And the text file just gives you the names corresponding to those indexes starting at 0. So this is like in Python, the first item is 0, the second item is 1, and so on. You have this utilities module here where you have functions to help you load the data and export the results. If you want to change anything in these functions, it's best if you copy the function to your own module and change it. Don't change this file because I will be assuming it's the same for everyone if I want to test the code. And then you have this TP1 text file. This is a plain text file with the questions for you to answer. All of those who did machine learning last semester already know this system. This is what I generally use. So basically, this is like the report for your assignment, only it must be in plain text and follow that structure so that I can more easily grade everyone and not have to deal with many different formats. This is an important file. Remember that a large part of the grade, perhaps more than half, will depend on what you explain here. This is not so much about coding and implementing and so on. It's mostly about understanding the problems, understanding the solutions, thinking about the different networks and such. And so it's very important that you give answers that are clear, concise, and show that you clearly understand what you are doing. So do not leave this just for the last day before submitting the assignment to do in a hurry, because this is an important part of the grade for the assignment. And then you have this tp1.py, the module that it will be the main file for your code. It's empty, you'll start filling it there. You can write other modules, so if you want to organize your code in different modules, that's okay. You can include them all in the zip file when you submit, but you need to have this one, which is the starting point, so I can test your code easily. When you submit the assignment, do not include this folder and do not include TensorBoard logs and things like that. Otherwise, the zip files will be enormous and there is no need for that. You can and should show the plots for training your networks, but do that creating images and not including the TensorBoard logs, even if you use TensorBoard, because that would make the submitted files very large and it's not necessary. And also try to keep your files at a small size, so no larger than 5 megabytes or something like that. So even if you create several images, think about which are the more important ones and don't overdo it. Okay? So this is the data I provide. You have in the utilities module a function for loading the data. You just call the load data, and this returns a dictionary with the training and test images. So this would be the training set is a matrix tensor with, it's not a TensorFlow tensor, it's just an NumPy array, but it has 4,000 images of 64 by 64 by 3. Then you have a test set that is separated, that has 500 images with the same format. You also have the masks for the segmentation. So these are 64 by 64 by 1, and they are just 0 or 1 to indicate where the pixels are for the Pokemon. And then you have the classes and labels. So the classes for training and testing are one-hot encoded, and you have 4,000 for training, 4,000 examples, and 500 for testing, and these are the rows of the matrix, and you have 10 columns, because you have 10 different types of Pokemon, and this one-hot encoding means that you have zeros everywhere, except you have a 1 on the position corresponding to the class for that Pokemon. Then you have the labels also, the training and test labels, and these are have the same shape and the same kind of encoding, but they can have more than one position set at one. So they can have 1 or 2 values of 1 there, because each Pokemon can have 1 or 2 types. So these will be used for the multi-class classification, the classes, and the labels for the multi-label classification problem. So you get a dictionary with all of these already processed. If you want to look at the code to see how they're done, it's okay. And if you don't want to use this function and process the data yourself, that's okay too. You're not. It's not mandatory that you use this function as long as everything works. But this one is just to help you skip these preliminary tasks of having to read the files and to understand how the data is stored and so on, so you don't waste time with those things. Then you have some functions that can help you export the images. The images are here in these arrays. You can use, if you want just to look at them while developing the code, you can use pyplot and plot the images on the graph, so on your console or on the plots tab on Spider. But if you want to save the images to a file, you can use this function where you give the name of the file, an array of images, and you can specify how many you want per row, and it will create an image file with all these tiles together. So for example, I'm creating a file with the first 20 images on the test dataset using 10 columns here. So this would be this file. You can do the same thing for if you send the masks here, you can also generate the masks. It works the same way, both for the images and the masks. You have also this function to compare masks. So let me see if I can show you here. You see that there are these colors here indicating where one mask has marked that point positive but the other didn't, or vice versa. So red and green show the two different possibilities. White means that both masks are in agreement, and black also they agree that there is nothing there. So here we can compare on the test set the ground truth, the original masks, and the masks I obtained after training the network. And this way we can see that things are fairly close to one another. So you can visualize what kind of errors your segmentation is making. Okay, so this is one way of looking at the result of the segmentation network. This is another overlay masks. You give a set of images and your predictions, and it will create a tile by putting the pixels outside your mask in a red and darker tone, and the pixels that your mask considered to be the Pokemon are brighter. So we can see this a bit zooming. We can see that there are sometimes the mask does not get exactly right, but it's mostly around the Pokemon with only some pixels missing or in excess there on the edges. So this also allows you to visualize how good the segmentation was. You can also create your own functions for doing this kind of operations. So take a look at the code, see how I did it, and create your own versions if you want. But the idea is that you have some easy way of looking at the results and seeing how things are going, because sometimes just looking at the loss function or some accuracy measure or something like that does not really tell us if we are getting things right or how wrong they are coming out, especially when you are dealing with segmentation where it's useful to look at the images. So what you need to do for the assignment is to think about the models you want to create, experiment with them. You don't need to create very complex models, because this is a small data set. It's easy to overfit. You only have 4,000 images for train and validation. You should leave the test set for evaluation at the end. But for doing training and validation, you can use those 4,000 images in whatever way you want. I would recommend using about 500 for validation and the rest for training, but you can think about that problem for yourselves. In any case, you need to experiment with some different models to try to see what works best for each of those problems. You can use the functional API on Keras if you want to do something a bit more sophisticated, where you have, say, parallel kernels or things like that. But I think that this can work fairly well with simple models. I tested a few simple models and it worked okay. So as long as you understand what you're doing and experiment with some different models, you don't need to implement anything very complex. Select the best one for each task, evaluate, use regularization, and so on. So you need to discuss what your reasoning was and how you try to optimize the network for solving each problem. So think about those different aspects that we covered so far. And one thing that is very important, you need to use the appropriate activations on the output of the network and the loss functions. These are three different problems. Multiclass and multi-label are different. Segmentation, you can think of them of segmentation as a kind of a multi-label classification problem where you have just binary labels at the end. But in any case, you need to think about the activations and the loss functions that you're going to use. You can use many different layers. These are some examples we already saw: batch normalization, convolution, and so on. You have this upsampling 2D that you can use for the segmentation network. If you want to do something similar to, for example, UNet, you will use pooling on the downward path as you decrease the resolution, but then you'll use upsampling followed by convolutions for the increasing the resolution. So you can combine an upsampling into dimension with a convolution of 2 by 2, for example, for doing the upsampling stage. And then, or you can use transposed convolution and so on. You have other options there in Keras. So check the documentation and see what is easy to use. You have lots of these different layers there. I tried to make this problem solvable even if you don't have very good hardware. So when training, this takes about 2.5 gigabytes of RAM. So if you have a 4 gigabyte laptop, you should be able to do this easily. If not, then you can use Colab. I think these networks do not take very long to train. And if you use Colab, you can select GPU acceleration and so on, and it makes things faster. So this should not be a problem at the hardware level, although since the training set is small, it's likely to have overfitting issues. So you'll need to think about your models. Don't create networks that are too powerful. Use regularization techniques and experiment a bit to try to minimize overfitting. So this is the main part of the assignment. Then there is an optional task, which is just worth 10% of the grade. So that's why I called it optional. Don't start doing this until you finish the rest, because this takes a bit more work, and it's only if you really want those additional 2 points. And the idea here is that you use pre-trained networks that are available in Keras, that were trained on the ImageNet dataset, and they are very powerful networks. So these can have from 5 to say 500 million parameters or something like that. So they can be very huge networks. I advise you to use only the simple ones like MobileNet, EfficientNet, and so on. These are designed for mobile devices, and so they don't take up too much memory, and they can be easily used in I think any modern laptop. If you go for the larger ones, make sure that you have hardware that can handle them, especially RAM, because if they take too much memory, especially during training, since you are feeding in batches of images, you need to have lots of RAM available. So for these, you can download them like this. The Keras applications module has several of them available. When you create one, if you don't have the weights locally, Keras will automatically download the weights and store them in a local cache. This include top false means that we don't want the final classifier head. So the dense layers are ignored, and we just have the convolutional parts of the network, which is what we want to transfer that feature extraction knowledge into our problem. You can specify the input shape. So in our case, it's 64 by 64 by 3. Not all of the networks available can take this shape because they are optimized for the ImageNet dataset. MobileNet and EfficientNet I tested and they work. Some of the others may not work. So look at them, see the documentation, or experiment. And then you have these, when you create one of these objects, I call this one core, you can call whatever you want, but they have the input and the output tensors. And you can use this to fit into your own module in the same way that we saw here for the exercise, where we create a new module using the inputs of the previous one and then connect one particular output of the previous model into a new set of layers that we're going to train. So you can do this sort of thing with the networks you download from the Keras library. You also need to pre-process images because these nets can expect images in a specific format. For example, mobile net expects them in values between -1 and 1. So the best thing to do is to use the preprocess input function that you have for each of these networks. You can see this on the documentation, but basically this preprocess expects to have images with values in the range of 0 to 255, and it outputs them converted, rescaled into -1 and 1. So I just input the training set here with this rescaling, and then I retain a copy of this this set of values, the images properly rescaled. So now I can use this to feed into the mobile net and get the features from the last convolutional layer, and then use that to train an additional classification layers with dense layers. Okay, so you have here a list of what are the available networks. You have the documentation showing how to use this, and the idea of this optional task is to use these networks to solve the multi-class and multi-label classification problems and compare the results with your original network. So see how fast they are trained, if you have more problems or less with overfitting and so on, and try to explain what you think is happening when you use transfer learning in this for these particular problems. Okay, so this, remember to freeze the original part exactly like you did in the exercise, because otherwise you'll be training a huge network with millions of parameters, and that can take a long time. So the idea is to use the pre-trained networks and freeze them so you don't have to recompute all the weights on the convolutional parts and just train the classifier head at the end. And then you discuss the results, what the comparison between what happens when you use this transfer of these networks into your problem, and compare it with what happened when you trained your own networks from the start. Okay, so to sum up, we saw the idea of transfer learning as a motivation for the functional API in Keras and the first assignment. You can submit your assignment from 18 of April to May 2. I'm going to give an extra 48 hours for problems, for fixing submission problems. So the deadline, the hard deadline, is May 4. And I can extend a bit the deadline for group formation. I don't know if everyone already solved the groups, but if you only start submitting the assignments after the 18, then we can I can keep the group formation online until 17, and you have more time to create the groups. But try to do this quickly, because otherwise you'll have less time to do the assignment together. Check the assignment instructions online, and I can update them if there are some questions or things that you don't understand. I can clarify in the online instructions, so take a look at them occasionally to see if there is something new there if you have questions. So for today, we're going to do this exercise on transfer learning using the fashionist network from last week. And you can take also advantage of today, since it's a lighter session, to catch up to anything that you left behind. So if you didn't do the exercise for last week, do it now so you can do the transfer learning. If you have questions about previous exercises, let me know in the Hangout so we can solve those. And the next 2 weeks, will be mostly reserved for the assignment. I think I will also give you some few exercises in the tutorial sessions, but it will be small exercises so that you have time for questions and for help with the assignment. Okay, so that's it for today. I'm going to log into Zoom, and we can and I can answer your questions if you have them in the live session. See you soon.